The modern Earth supports life everywhere, from deep caves in the upper atmosphere to volcanic regions, but for most of its history, this planet was nearly uninhabitable. Today, animals, plants, fungi, and bacteria have all evolved to adapt to various extreme environments. This widespread distribution of living organisms makes it easy to assume that this is a planet with naturally favourable conditions. However, physical evidence reflects a completely opposite reality. For billions of years, most of Earth's surface was nothing but dark, hot, frozen, or nearly desolate regions. Today's rich ecosystem was not naturally present, but is the mechanical result of a long chain of mutual transformations among geological structure, climate, and biological evolution. This raises a question. The earliest stage to verify this primitive state is the Archean Eon, which began about 4 billion years ago and lasted for approximately 1.5 billion years. This period opened right when Earth had just undergone the late heavy bombardment. Thousands of tons of rock fragments from the formation of the solar system continuously crashed into the planet, releasing kinetic energy that fractured the thin basaltic crust newly formed on the magma surface. Subsequently, Earth cooled down and formed the first lithosphere. However, an environmental limit emerged as it took about 1 billion years later for the first living organisms to appear. This delay stemmed from the fact that Earth's surface during this period was very simple, with a relatively flat topography. Because tectonic plates were not yet operational, the planet completely lacked high mountain ranges created by plate collisions. The rock composition forming the lithosphere was also highly impoverished. Most of Earth's crust was merely basalt, essentially magmatic lava, that had solidified, leaving new mineral deposits and rock types in only the earliest stages of formation. Interacting with this basaltic crust was an atmosphere almost entirely devoid of oxygen. Simulation data indicate that nitrogen concentrations were lower than today, while the atmosphere was dense with water vapour, carbon dioxide, along with oxides of sulphur, phosphorus, and many other chemically active elements. These gases increase the environmental acidity, creating a barrier to the stability of organic compounds. Surface mechanical conditions were further complicated by parameters from the Sun and the Moon. At this time, the Sun was fainter than at present, with a luminosity about 30% lower. Conversely, the Moon was positioned much closer to Earth, causing gravitational forces to exert a very strong impact. This gravitational pull, combined with a high self-rotation speed, meant that a day lasted only about 10 hours, while simultaneously triggering massive tidal waves ranging from several tens of meters up to 300 meters that continuously swept the surface, obliterating physical stability on a large scale. As the planet continued its cooling trend, the massive amount of water vapor in the atmosphere condensed into torrential rains. This water accumulated in the depressions of the flat basaltic crust, forming the primeval water bodies. Due to the direct absorption of oxides from the atmosphere, the initial ocean was highly extreme, characterized by acidic, saline, and boiling hot water, with some areas near the boiling point. The water composition of this period was identical to modern hydrothermal vents or geysers. This harsh environment paradoxically became the cradle of primitive life. Since oxygen did not yet exist in the atmosphere, the first organisms were obligator, anaerobic, maintaining metabolism without oxygen and relying instead on alternative chemical energy sources. Due to structural limitations, Archean organisms were unable to swim, forcing them to adhere to a lithospheric substrate to survive, preventing them from being swept away by mechanical tidal forces. Consequently, the biosphere during this period was extremely thin and narrow. Life existed only as a mucus film, no more than 1 millimeter thick, situated at the bottom of the hot acidic ocean in coastal zones. The maximum depth of this layer was strictly limited to approximately 20 meters, because the dense atmosphere created an optical barrier, preventing sunlight from penetrating deeply into the lower water columns. In contrast to the shallow waters, deep-sea volcanic vents served as habitats for chemolithoautotrophic bacteria. This group of organisms operated entirely without light, deriving energy directly from chemical reactions between sulfur and iron compounds. As the planet continued to cool, sea levels rose, the atmosphere thinned, and the sun radiated more brightly. allowing coastal areas to become more favourable for the gradual expansion of life. However, by the end of the Archean Eon, the biosphere remained strictly confined to a narrow coastal band and small oases near deep-sea volcanic vents. The entire landmass, river systems, and most of the open ocean remained completely devoid of life. The only biological signature visible to the naked eye in the geological record is stromatolites, sedimentary limestone structures constructed by ancient microorganisms through mineral binding mechanisms which could reach heights of several meters. Early evolution was severely limited due to the deficiency of necessary reactants. The ecosystem at this time did not yet have decomposers or scavengers to release organic matter. When organisms died, their carcasses accumulated in depressions on the seabed due to the effects of gravity and ocean currents. Hundreds of millions of years later, these buried organic accumulations were naturally transformed into petroleum deposits. This state was disrupted around 3.12 billion years ago, according to the original content, a time when organisms emerged that profoundly altered the Earth. This was when certain bacteria began to develop a photosynthetic mechanism and produce free oxygen. About 1 billion years later, at the boundary between the Archean and Proterozoic eons, the oxygen revolution triggered a massive global extinction. This event is known as the Great Oxidation Event. The actual scale of the damage is highly difficult to estimate, precisely because most organisms of that era were not preserved as fossils in the sedimentary record. However, the intense oxidative pressure caused almost the entire diversity of anaerobic organisms, which had taken about 1 billion years to evolve prior to that, to completely disappear. The ancient atmospheric environment during this period was naturally very rich in methane, a potent greenhouse gas that helped maintain stable temperatures. When oxidized by the increasing amounts of oxygen, methane produced carbon dioxide and water. This mechanism caused the greenhouse gas content to plummet. As the methane concentration decreased, global temperatures dropped deeply, leading to the Huronian Glaciation. The event is described as the largest scale ice age in Earth's history. Beginning about 2.4 billion years ago and lasting for approximately 300 million years, this phenomenon established an extreme thermal equilibrium state. Geological evidence indicates that in some areas, ice sheets extended all the way to the equator, causing the planet to nearly turn into a snowball Earth. Earth underwent an extreme transition from boiling lava fields to vast, sweeping frozen deserts. This process of geological and climatic transformation took place over a span of about 1.5 billion years. This condition blanketed the early stage of the Proterozoic eon, a geological eon lasting from about 2.5 billion years ago to 440 million years ago, according to the original content. During this phase, despite the freezing conditions, life managed to persist by relying on rudimentary adaptive mechanisms. Evolution continued to occur but was severely hindered by low temperature limits. The land remained completely devoid of life, forcing organisms to concentrate primarily in coastal zones near the equator, the only locations with the minimum thermal energy necessary to maintain liquid water. On the continents, metal deposits and new rock types continued to form through endogenous geological reactions. The terrestrial surface shifted constantly, at times existing as glaciers, and at others as rocky deserts. Around 500 million years ago, due to the complete lack of vegetation, most of Earth was described as resembling a Martian desert. This state changed only when the sun grew progressively brighter and warmer according to the stellar evolution cycle, causing the ice to gradually melt, paving the way for a new geological eon. About 542 million years ago, the Phanerozoic eon officially began. The term Phanerozoic signifies the eon of visible life. This was a period marked by biological evolution, occurring with intense momentum. However, this progression did not unfold continuously, but instead comprised phases of biomass expansion interspersed with mass extinctions. Regarding the tectonic geographic structure at the beginning of the Paleozoic era, the majority of the planet's landmass merged into the supercontinent Gondwana. This massive land block was positioned in the southern hemisphere with a surface area of over 100 million square kilometers, encompassing the component regions that today make up Africa, South America, Antarctica, Australia, the Indian subcontinent, and several other areas. Meanwhile, smaller scale continents, including Laurentia, Baltica, and Siberia, were located near the equator, surrounded by the appearance of numerous small islands. The distribution of these continents could not yet facilitate the expansion of the biosphere onto land due to adaptational limitations. Up until the Huronian period, according to the original content, which began about 444 million years ago, the land had almost no significant life forms establishing a foothold. The sedimentary record of this phase indicates that only a few species of simple mosses and lichens began to appear to generate the earliest rudimentary biomass. Moving into the early Huronian period according to the original content, the first plants emerged in tidal zones and near rivers, but their distributional range was strictly constrained as they only appeared within tropical regions. Even though marine organisms and plants during this stage had become more diverse, the oceanic ecosystem still endured physical limitations. Marine life remained primarily concentrated in coastal zones because the deepwater layers had not yet optimized optical parameters. Crucially, in the Devonian period, the ocean depth where the process of photosynthesis could take place was restricted to a level of about 50 meters, equivalent to 1/10 of the modern parameter. Within this same geological timeframe, according to the original content, a phase starting from 420 million years ago and extending to 359 million years ago, the ecological link underwent a shift when the first decomposers appeared. They assumed the function of breaking down organic carcasses, settling to the bottom, establishing the necessary conditions for organisms that feed on decomposition products to develop. The appearance of decomposer populations in deep water strata established a new dynamic link, setting the stage for the transition to the Carboniferous period, a phase lasting from 358 to 299 million years ago. As this period opened, the majority of the tropical zones on Earth were covered by large-scale forests of tree ferns. However, an ecological mechanism contradiction emerged. The Carboniferous forest system lacked the participation of effective wood-decomposing organisms. The direct consequence was that tree trunks after death could not rot through natural cycles, causing the phosphorus content accumulated in plant tissues to be locked away, failing to return to the soil to nourish the next generation of plants. This blockage of the nutrient cycle caused the lush forest to gradually shrink in area, giving way to massive accumulations of dead wood built up progressively over time. Under geological compression, these organic masses later formed rich coal deposits, a fuel source that remains widely mined and utilized by humans in numerous industries today. The development of woody plants during this era was strictly constrained by geographic factors. Outside the tropical zones, the vegetation consisted only of fungi, mosses, and lichens. Due to their rudimentary structures, these organisms lacked root systems capable of holding surface soil firmly, causing the terrestrial environment to fall into a state of mechanical instability. Whenever it rained, soil was easily washed away, turning river systems into thick mudflows, transforming water-retaining lake basins into foul swamps due to a lack of dissolved oxygen, while arid zones quickly turned into dead deserts because they could not retain moisture. This terrestrial geological instability simultaneously created a barrier for aquatic ecology. In the seas and rivers, fish evolved very aggressively in terms of species diversity. However, life was still unable to advance into the open ocean. This limitation existed because the algae species of this period had not yet learned how to float freely on the water surface to photosynthesize, leaving the energy source of the food chain confined and restricted to coastal areas. The Permian period followed immediately after the Carboniferous, beginning 299 million years ago and ending at the mark of 252 million years ago, according to the original content. In this stage, the first amphibians began moving to explore the land, while plants also adapted to spread into subtropical regions. Despite this, life within the seas remained primarily distributed in shallow waters near the coast because the floating limitation of algae had not yet been overcome. The Permian period closed with the largest mass extinction in the history of multicellular organisms. The pressure of this event wiped out up to 96% of marine species and 73% of terrestrial species entirely, while the exact cause of this extinction event has yet to be determined with certainty by any scientific model. Following the Permian extinction catastrophe, the Triassic period quickly brought about the recovery of life and shifted it to a new level of development. For the first time in Earth's geological history, temperate latitudes recorded the appearance of forest systems breaking the distributional limitation that had restricted them solely to tropical regions during previous eras. This ecological structural shift occurred simultaneously with a biological revolution in the marine environment. This was marked by the appearance of blue-green algae and cyanobacteria, with structures identical to their modern descendants. The core evolutionary step of this group of microorganisms was that they no longer needed to live attached permanently to coastal lithospheric substrates as they did in the Archean or Paleozoic eras. The capacity to float freely allowed photosynthetic microorganisms to spread rapidly and occupy the entire surface water column of the global ocean, releasing a massive amount of biomass into the open water system. The direct consequence of this primary producer boom was an unprecedented expansion in the scale of the marine food chain. Species of fish, mollusks, and arthropods rapidly migrated far from the coast to follow the new, abundant food source. When these populations died, organic remnants settled to the deep seafloor in massive volumes, providing a superior source of nutrients for benthic organisms that previously had always faced food shortages. This mechanism helped the global ocean gradually take on an appearance and physical operational mode closely resembling those of the present day. All of these shifts shaped the Mesozoic era, a geological era lasting from 250 to 66 million years ago, comprising 3 consecutive periods: the Triassic, Jurassic, and Cretaceous. This was the era that witnessed the powerful development of dinosaurs. However, real-world data correct a common misconception in older simulation models, which was that the Earth during the age of dinosaurs was completely covered by continuous tropical rainforests from the poles to the equator. In reality, the climate system indicates that forests only reached northern latitudes because the global average temperature was higher than it is today. Conversely, the equatorial region suffered from prolonged drought conditions, leaving the Earth of this era still retaining numerous swamps and deserts. The desert systems back then were highly diverse in terms of meteorological parameters, featuring not only hot and dry types, but also temperate, cool, and humid deserts. Because herbaceous plants had not yet evolved, the soil lacked an interwoven root system and was therefore very difficult to bind firmly to rocky slopes, resulting in only lichens being able to grow on bare rock surfaces. The distributional limitation of vegetation on the bare, rocky slopes of the Mesozoic era began to be overcome when a new biological mechanism emerged. Flowering plants became widespread during the mid-Cretaceous period, approximately 100 million years ago. The earliest evolutionary forms of this group were predominantly woody trees, which did not yet produce a significant mechanical impact on the large-scale structure of land topography. The real turning point occurred during the late Cretaceous period with the appearance of species resembling modern herbaceous plants. This structural modification brought a special role for grasses and herbaceous plants in shaping the lithosphere and hydrology. Unlike the preceding moss or lichen structures, the small and dense root systems of herbaceous plants wove tightly into the ground, triggering a mechanical binding mechanism that helped form and consolidate the surface turf layer. The emergence of this biological mat made the soil more durable, preventing it from being washed away and eroded by the physical runoff impacts of rainwater. On the hydrological side, this root system and vegetative cover helped transpire excess water through leaf evaporation, while simultaneously retaining necessary moisture for the soil when the environment entered an arid state. This optimization of water retention conditions directly altered the structure of surface ecosystems. When herbaceous plants appeared, previously arid desert regions transformed into steppes, grasslands, or savannas. Stagnant swamps converted into flood meadows, while permafrost regions turned into tundra and tundra steppes. By the end of the Cretaceous period, owing to the mechanical and hydrological transformations driven by grasses, the surface structure of the Earth began to resemble that of the present day. Although the geographic appearance had been shaped, the global ecosystem had not yet reached its modern state because it still lacked a crucial biological component: widely developed mammals. However, a biological pressure contradiction emerged as they were unable to become widespread until the very end of the Mesozoic era, due to the dominant control over energy and resources held by large reptiles. This evolutionary freeze was only disrupted by a planetary upheaval event, although the exact cause of the dinosaur extinction remains not completely clear according to the original content. Current scientific models offer various hypotheses, including the impact of a giant asteroid, global cooling, or other physico-chemical causes originating from within the planet itself. The direct consequence of the dinosaurs' disappearance was that all major ecological niches in terms of the food chain and living space were left completely vacant. The release of these competitive pressures provided mammals with the opportunity to thrive robustly in both population and size to fill the structural gaps in the ecosystem. Throughout the next 66 million years, natural selection pressure drove a profound chain of diversification. From initially small organisms with marsupial-like characteristics, mammals evolved mechanical and functional adaptations to split into several major groups with completely distinct lifestyles, including whales in the ocean, tigers in the terrestrial predatory niche, camels in arid regions, and bats occupying the atmospheric space. The diversification of mammal groups into vacant ecological niches established the modern biological structure. Ultimately, the process of evolution produced Homo sapiens, or humans. This emergence brought about a major contradiction to preceding biological laws, as humans are a distinct species with a completely different operational mechanism, not merely stopping at adapting to nature, but also possessing the capacity to actively change nature. The foundation for this transformation stems from humans directly exploiting the geological legacies of the past. A prime example is coal, which was formed from dead trees that accumulated without rotting millions of years ago under the compressive pressure of the lithosphere. Humans burn this fossil energy source to serve heating needs and operate industries, releasing carbon compounds back into the atmosphere at a rate much higher than natural geological cycles. The consequence of this intervention capability leads to a severe reality of ecological upheaval, as the original content offers a direct critical perspective against anthropogenic behaviours. Humans destroy other living species solely for commercial purposes or sport, severing food chains that took millions of years to shape. At the same time, overexploitation driven by selfish motives has transformed vast, once lush lands into dead deserts, accelerating the erosion rate of the surface topography. This reversal of mechanisms clarifies the concluding significance of the entire chain of geological data. The history of Earth is inherently a prolonged process where life must continuously find ways to adapt to a planet always in flux regarding both its lithosphere and atmosphere. But ever since humans appeared, life is no longer in a passive stance, but has begun to become a physical force that can directly impact and actively reshape the planet in return. Analysing the entire sequence of geological data and evolutionary mechanisms from the Archean Eon to the rise of Homo sapiens requires the synthesis of complex scientific models. Please like the video if the causal parameters just mentioned clarified your perspective. At the same time, please leave a comment and share your thoughts in the discussion section regarding the limits of human intervention on the planet. Your feedback is crucial data for the channel to continue improving quality and support future videos. Thank you for watching. See you next time.